Hi everyone, we're doing this video for course 2IMN15, Internet of Things, from TU Eindhoven. We are group 5. Our topic is Deep Learning in IoT. This presentation is based on paper Deep Learning and some other references. In many ways, the technological progression of AI and the IoT are intertwined. Here's a metaphor. IoT will provide the information that fuels our data-driven economy, while AI is the engine that will consume it. Though both paradigms are still in their infancy, each success is contingent upon the others. A lot of IoT devices gather data from their environment. That data needs processing. Using deep learning techniques, useful information can be distilled from the raw data. IoT also involves a lot of human interactions, such as objects that you can control with your voice or that perform an action when a human appears. Now we will give some brief introduction about machine learning. Other than reinforcement learning, machine learning can be divided into two main categories. Supervised learning, where a model is generated that produces a desired output for a given input. There are two types of supervised learning. Regression, where the output is continuous values. So for example, predicting housing price based on the old house information. For classification, the output is discrete. Examples of this include to classify an image is of a dog or a cat. While unsupervised learning is when there is no desirable outcome. One class of unsupervised learning is segmentation. For example, determining different types of customers from usage data of a web shop. Another usage is anomaly detection. For example, in a manufacturing plant, anomalous outputs should be detectable. Hebbian learning is biologically inspired way of changing weights and biases in a neural network. While deep learning is in the field of machine learning that concerned with training deep neural networks. With multiple hidden layers, the structure is trained using numerous labeled data. In this presentation, we will present two powerful deep learning architectures and look at how deep learning techniques can be applied in IoT in practice. Notably, this video is more an overview than an in-depth presentation. If you are interested in this subject, we encourage you to check out the links in each page. They have helped us a lot in understanding this subject.
Before we start with more complicated architectures, we will explain a little bit about artificial neural networks. Artificial neural networks are inspired by the brain. Like neurons in the brain, artificial neurons get a stimulation from other neurons and based on the sum of this stimulation, produce an output. These inputs are multiplied by weights and there is often bias added to this sum, which also has a corresponding weight. And then there's an activation function, which can be a unit step or a sigmoid or other functions. Most neural networks are divided into layers, and the outputs from neurons in a layer are only connected to the neurons in the next layer. And there's always one input layer and an output layer, and there can be multiple hidden layers in between them. The input layer simply outputs its input to all connected neurons in the next layer. So if we are going to use this network for example, for predicting housing prices, we need the input of each feature in the input layer. We need to input each feature in the input layer. So as input of the first neuron, we set the floor area, for the second, the amount of bedrooms, and for the third, the garden area, etc. And then we calculate the activations of all neurons in each layer. And the output of the output layer will be our predicted price. The first time we do this, the prediction is of course completely wrong, and in order to make a good prediction, we first need to train the network. That is, we need to change the weights and biases. So how do we do that? We do that in two steps. The first step, we apply inputs at the input layer of the network and then calculate all activations until we come up with an output, and then we compare this output to our desired output and calculate the error, and we propagate this error back to previous layers up to the input, and then we try to change the weights and biases so that this error will decrease. So if you want to know more about how this works, I suggest you check this link or the Coursera. They're both really explain this really well. Now we can go on to more advanced architectures. The first one is the recurrent neural network. So the problem with ordinary neural networks is that they do not have memory, and some tasks that contain sequential data profit a lot from having memories. For example, speech processing, the words in a sentence are really dependent, and so having memory is useful. So how does a recurrent neural network work? This is quite simple. In a recurrent neural network, there's one extra output, and that output is fed back to the input with each next item that is processed. So in this picture, we should note that the arrows are not scalars but are vectors, and the image on the left is how it actually the actual architecture, and the picture on the right is if it's unrolled, and then x0 is the first time you put an item in it, and x1 the second, and so on. And there are multiple architectures for this unit, this A. In the next slide, I will discuss one, which is called the gated recurrent unit. Here, HT is the state of the neuron, and it's also the output in this case. And we can see two interesting things here. The sigmas are gates, and they output a number between 0 and 1, and these gates determine how much of the state is considered by the network, and they also, the other sigma decides how much of the output is determined by the state, by the previous state, and how much is determined by the current output of the network. And the sort of network in this case is the 10H box. So applications for IoT, they could, for example, be used for traffic prediction, but of course they're really suitable for natural language processing, and in this way you can make, for example, smart objects that you can have a conversation with. The second architecture is the convolutional neural network, and this type of network is mainly used for image classification. There are three key concepts behind convolutional neural networks. The first one is local receptive fields. It sounds a bit hard, but you should compare it like shining a flashlight over the image. So you consider a small part at the image at a time, and then you shift your flashlight so to consider all parts. And then there's shared weights. So for every shift of this flashlight, you keep the same weight. And then after this convolution, which is the shining of flashlight, there are activation or pooling layers, and there the output from the convolution filter is fed through a more ordinary neural network. And so often these convolution and activation and pooling layers are combined. And after this sequence of convolution and activation, there is an ordinary neural network to determine the class of input image based on the features produced by the network. They're mainly applied for image classification, but have also been successfully applied in speech recognition. These are two very useful applications for making smart objects. So what have we learned? We have seen how neural nets work, and we have looked at recursive neural networks, which are good at sequential data, for example, natural language processing, and we've looked at convolutional neural networks, which are good at image classification. And we've seen that both recursive neural networks and convolutional neural networks have a lot of interesting potential applications in the IoT domain. And well, both domains, both IoT and AI are continuously developing, so they will develop together to make a really happy future, hopefully.
From now on, we will discuss about AI for embedded IoT. Here's a brief content. So why do people have to implement deep learning techniques in embedded IoT system instead of put them in cloud? Well, deep learning applications on IoT devices often have demanding real-time requirements. Commercial smart IoT devices often offload intelligence to the cloud. Nonetheless, consistent good quality network connections, which are only available at limited locations at high costs, become a challenging constraint for these devices to abide by real-time requirements. A better choice is to enable deep learning on these devices, which isn't affected by the connection quality. This is also safer from the data protection consideration. More importantly, is because of the resource constraints. These slides introduce the most common system resource bottlenecks of embedded systems, like limited memory, limited computational power, and limited bandwidth and limited energy supply. While implementing deep learning techniques into embedded systems, these constraints should be considered. First, we will introduce some algorithmic solutions. One of the possible ways is to start with a large net, then prune it to a desired size. This year, DeepScale and UC Berkeley and Stanford University has released an architecture called SqueezeNet. We will introduce its benefits in the next slides. And also, ARM recently announced their Common Compute Library, which contains a lot of comprehensive collection of software functions. SqueezeNet as a small CNN architecture has 3 advantages. More efficient distributed training. Communication among servers is the limiting factor to the scalability of distributed CNN training. Small models will train faster during requiring less communication. Less overhead when exporting new models to clients. Less overhead when exporting new models to clients. For autonomous driving, companies such as Tesla periodically copy new models from their servers to customers' car. This practice is often referred to as an over-the-air update. However, over-the-air updates of today's typical CNN models can require large data transfers. Smaller models require less communication, making frequent updates more feasible. Feasible FPGA and embedded deployment. FPGAs often has less than 10 megabytes of on-chip memory and no off-chip memory or storage. For inference, a sufficiently small model could be stored directly on the FPGA instead of being bottlenecked by memory bandwidth. Also, there are a lot of evolutions in the hardware side, both in the server side and the embedded terminal side. For example, NVIDIA has GPU, which is the most widely used platform. Intel also has Navina and Movidius. IBM has Watson and TrueNorth. Google has TPU, and ARM has Dynamic. Also, there's also a new company in China called Capricorn, who has invented very powerful AI chips. Here are the papers that we referred in this presentation. Thank you for watching our video. Bye-bye.